We have a polynomial rational expression. That means a polynomial stacked with a fraction, if you will. We're going to try to graph it eventually, and you can always try to graph it first, but if we can find some key points, it'll make the graphing easier. Now again, you'll normally have a graphing calculator to check these things, but we want to be able to see if we can find them algebraically. So when we talk about x-intercepts are what make the equation go to zero. It can usually be helpful if you ever see anything you can factor, you should do it. So the top would factor to x plus 3 times x plus 5, and we'd leave our x plus 3 in the denominator. This will help us see things a little bit easier. Now, x-intercepts come from when the numerator goes to 0. So, highlight here, what would make each of these bubbles go to 0? Because if we plug it in, 0 divided by anything will be 0. First thing we can say would be our negative 5. That's plus 5 there. So we'd have negative 5, 0 is one of our zeros. And we would say probably that negative 3, 0 is. Now, in a moment, we're going to talk about this. This is kind of a special case. But always look for when your numerator goes to 0. That will be your x-intercepts. Your y-intercepts are what you have when your x is 0. So if I were going to look at if x were 0, if I put zeros in for all of this, the only thing left would be these two terms. Okay, so let's highlight that here. If I had these two right there, these would help me find my y-intercepts. That's because when you put 0 in for x, all the rest go away. So you'd have 0 is x, 15 divided by 3 is 5. Your y-intercept will be 0, 5. Now, vertical asymptotes. Those are where the graph cannot touch. So it kind of make a line that's like dashed down your graph and it won't be able to hit that. When we look for vertical asymptotes, we look for when the denominator goes to 0. Now in this case, we have a unique situation. Notice how our top and our bottom of our fraction have the same factor. Those technically would reduce. So in normal cases, a vertical asymptote is what makes your denominator 0. Well, negative 3 would. The only trick is negative 3 is also in the top as a 0 for our x-intercept. So the question is it an x-intercept? Is it an asymptote? It surely can't be both. When we look at the graph, I'm going to drag a Desmos graph over here for you of the equation, again, just to kind of get an idea. If you look, here's my equation. I'm at negative 3. I've zoomed in a lot. Watch when I trace along here. Negative 3, really close. When I get to the actual negative 3, it says negative 3 undefined. Right there you can see that open circle. That's what happens, that's what happens when you have a numerator and denominator factor cancel. So back to our graph here, our equation. These canceling means that there's actually a hole. So for us, there's not going to be any vertical asymptotes this time. If there were, it'd be what makes your denominator 0. But since these cancel, that doesn't count. Which also means, since they cancel, this x-intercept doesn't count. Now, horizontal asymptotes are what happens as the graph goes out to large and larger numbers. So we want to look at the first terms of the polynomials. The top one is an x squared, the bottom one's an x. Squaring a number is way more powerful. So when your numerator has a higher power, we say that the graph goes to infinity. So kind of your horizontal asymptote is infinity. It's just going to keep rising up there. There isn't a set number that the graph's going to level out at. When it comes to domain and range, we're looking for domain is the x values you can plug in. Range is the y values that are outputted with the equation when you graph it. When we look at that graph, if we would go to our next slide here, if I'm going to graph this, we know negative 3 is our problem area. And sorry, back here when you're factoring, when x plus 3's go away, all you're left with is y equals x plus 5. So your graph is going to look like a line, y equals x plus 5. So if I graph that, there's my 5, I go up over that. The only trick is when I get to negative 3, there's going to be that hole there. So this would actually be my sketch of my rational function. Now, when we talk about domain and range, what x values are working on here? All of them except for that negative 3. What y values are working on here? It would go way up and way down, but the only y value that's not working there is that negative 2 for the y value. So that'd be the y value that's not going to work. So when we go back to domain and range, we would say all except x equals negative 3 for this one, And the range would be all except x equals 2. If you're looking on a table on your graphing calculator, it'll be where there's an error for either that x or y value.